Morning everyone. So we're going to continue our study into periodic trends. Today I'm hoping to cover three other properties with you. Remember, these are all physical properties that in organizing the periodic table in this fashion, we can actually start seeing some of the other patterns on this periodic table. One of the most important properties that we did from yesterday, basically roughly having our periodic table in the schematic here, we saw that in terms of the size, the radius, I had wrote down radius increases to the lower left corner. Just to give you some variety here, if I point in this direction, you should be able to translate here that the radius actually decreases. Remember, there's a lot of explaining style questions in this chapter. Your explanation cannot be, oh, I've just memorized this side is tiny and this side here is large. In this case here, your reasoning, as I go up in the direction that I pointed it, up actually implies that I have less shells. If I were an element that has 2 shells, I'm smaller than someone that has 5 shells, even though they may have more protons than me. As I go to the right, I may be all on the same energy level, I may be on the same energy shell, but what's going to happen here is I pick up protons going across, the electrons also get added in, but they don't shield each other from the next one that's being added. We actually have a greater Z effective. If you can quote the terminology that we've been using, that way you don't need to explain, oh yeah, after you add this electron here, you subtract off the screening or whatever. If you can use the vocabulary, even better. So today, again, I want to emphasize for you 3 other trends. We're going to do a trend called electronegativity, electron affinity, and we're going to end off with melting point. I pulled out 2 pages from your data booklet again. In your data booklet, again, it's laid out like a periodic table, but unlike the section 6, where you actually have the molar masses that you're used to, here's a table of melting points. We'll come back to this at the end of the chapter. At the end of the lesson here, and then we'll come to this other chart here, super useful, section number 8. Earlier we had talked about ionization energy. They qualify this as the first time that I removed an electron. Remember, the representative equation is taking the element, make sure you specify it's a gas, and with the pair of tweezers, I remove that electron and I let that go to infinity. The first ionization energy based on their formatting is in the top left corner of the element. So if I track these numbers here, you actually did this on your lab. Lithium starts off with 520, then it goes 900. These are all ionization energies. The units, sometimes they will just say, let's say, what's this, 801? Sometimes they'll say just kilojoules. But remember, in the technical definition of ionization, you would have lined up an Avogadro number. You're not just pulling off an electron off a single atom, but you're doing that process to everything in the atom, so it is understood that it's kilojoules per mole, even if it doesn't specify. We see that these numbers here gradually increase, and that matches up. Because our atoms tend to get smaller going in that direction, it's going to get much harder removing this electron as the radius itself gets smaller. So that's the trend for ionization energy. I'm hoping to do with you electronegativity first, then electron affinity. You see both of these values are on different parts of this element square, but we'll go from there. So let's just call this here first trend for today. We're going to do a guy called electronegativity. We haven't seen this guy yet. So electronegativity, I'm going to shorthand to EN. I'm going to start off with the definition. Electronegativity, although it's kind of named a little bit strangely, electronegativity is a measure of attraction for electrons in covalent bonds. In some sense, we're going to be using an analogy. It's sort of a tug-of-war. Even though electrons are supposed to be shared in covalent bonds, elements, based on their size, they may have different strengths in actually hogging the electrons towards themselves. So in this case here, this is actually what makes us either ionic or covalent bonding. I'm going to start off with the element, let's say chlorine and chlorine. We can go to our trusty table, just looking at the numbers for now. Electronegativities are on the bottom of each of the elements here. Chlorine has electronegatividity of 3.2. Don't worry about the units. It's on something called the Pauling scale. This 3.2 is a number that describes how hungry they are for electrons in the bond. So in this case here, for a diatomic molecule, we're going to see in the next chapter 2 electrons make up a bond. Although we're supposed to be sharing these in a covalent bond, the 3.2 actually indicates to me how much of an attraction I have on these electrons. Because chlorine is tug-of-warring against himself, 3.2 and 3.2, in this case here, although these ones here are absolute electronegativities, what I really care is between this tug-of-war, between these sharing of electrons, I want to see whether there's any difference in electronegativity. I want to see, is this a fair competition or not a fair one? And all you're going to do is just big number minus small number. In this case, they're the same. The difference is 0. We're basically saying, hey, it's chlorine fighting against chlorine. Nobody's going to win. what I want you to think about here is what feature of chlorine actually gives chlorine this electronegativity. What can I change about chlorine to make it more attractive for the electrons or less attractive? If you remember back to our principles here, our attraction to the electron actually depends on our number of protons. So for example, chlorine happens to have 17 positives in the core. Those 17 positives definitely will have some attraction on the 3 shells of chlorine that it actually has, but we're going to mainly focus on, I have 17 positives, I'm having to reach 3 shells out, and I'm trying to share these electrons with another chlorine that's 17, also trying to hog the electrons. We're thinking here Coulomb's attraction here. Remember, we're going to be using the relationship, but not actually punching in any numbers. We're going to use this relationship here where if I want the force of attraction, if I want to tug of war these electrons better, I want to have essentially more charge. So if I were comparing, let's say, chlorine, let's compare it to one element over, I think it's argon, which has 18 protons. Oh, I have more charges. I might imagine argon should have a stronger attraction. In that case there, you actually realize on your table, noble gases actually aren't given electronegativities. The reason for that here is because even though this is going to be a tug of war, this is going to be how attractive you are for the electrons, there is this caveat here, it has to have already been in a covalent bond. Noble gases already keep to themselves. Noble gases don't form bonds. That's a slight simplification. We've actually figured out with the really heavy noble gases, you can actually force them to bond. But overall, because they don't form bonds, there's no sense, let's say we have argon, yeah, it may be a tinier element, yeah, it may have the extra protons, it could potentially have tug-of-war electrons better, but because it doesn't take a bond, there's no point in giving me that number. In this case here, we're going to see in the next chapter, when your difference is fairly small, we're going to refer to this as covalent. And in fact, this one here, because we're totally even sharing, we're actually going to refer to this type of covalent as non-polar covalent. We are sharing electrons, but there are no poles. There's no unevenness. It's perfectly 50-50 of a split, okay? The electrons don't spend more time with one than the other. So that's non-polar covalent. Let's go to the opposite extreme here. Let's compare Na and Cl. Again, we're going to come back in chapter 4 to actually figure out all these Lewis diagrams. But so far, you should be able to tell sodium is in column number 1, so it has 1 valence electron. Chlorine, technically column number 17. If you skip those 10 D electrons here, group 17 is group 7, meaning chlorine has 7 valence electrons. These two have to first collide. Sodium is a fairly large atom because it's on the left-hand side of the periodic table, has less protons, smaller Z effective. Chlorine is on the same row, but with that extra number of protons, it can actually be a tinier atom. They collide together. Potentially, it's going to be the unpaired electrons that do the bonding. So that's these two here. We have to look at this property electronegativity to figure out, is this going to end up being shared, or is this going to, as we probably know, actually form an ionic bond? So let's have a look at the numbers again here. Chlorine has that electronegativity 3.2. That's a constant because chlorine will always have the same number of protons, same size to it. Sodium, being a much larger atom, it only has a 0.9. So in this case here, sodium's absolute electronegativity is 0.9. Chlorine is 3.2. Again, what we care is not necessarily these absolute values. We care about the difference. We care, is this tug-of-war even? Is it a heavyweight against a heavyweight? In this case here, there's no contest. If I go big number minus small number, 3.2 minus 0.9, I'm getting 2.3. I notice it's heavily imbalanced, and usually what we do is we point towards the winner. Chlorine wins, so chlorine hogs these electrons. Even though these electrons were supposedly shared, the chlorine is pulling so hard, it's tug-of-warring against someone who really can't fight against it, and actually, when this difference gets to be large enough, chlorine completely snatches the electron. When it completely snatches the electron, sodium is now down an electron. It's now a positive charge, square bracket with the charge in the corner. And then chlorine here, it used to have 7 electrons, but now I've gained 1 extra electron, and now I have a negative charge overall. Suddenly, we become an ionic bond because the tug-of-war is uneven. You might be wondering to yourself then, well, how big do I need to actually become covalent? That's actually going to depend on the exact molecule itself. Let me see if I can get rid of these ones here. Okay, so it's actually going to depend on the exact molecule, the average electronegativities, but usually we throw around a number. If the difference gets to be somewhat around 1.8, Anything smaller than 1.8 might be a slight imbalance. We'll call that a polar covalent compound, whereas something that's ionic is going to be the difference more than 1.8. The heavyweight competitor is actually pulling so hard, he actually completely snatches the electrons to itself. We're going to come back to this diagram a little more in chapter 4, but at least this is what this physical property tells us. Based on the periodic trend then, without actually looking at our data booklet and actually looking at the numbers, I want you to be able to predict for me which way would electronegativity increase. Most of the trends, as you start to see here, is they all rely on radius. So if I know the radius here starts really large, I'm big number of shells, not a lot of protons, and I tend to get smaller and smaller going down this way, it's actually a notable difference. When I think F is equal to kq over r squared, in terms of the size argument, I want to be small for me to have a strong force, not only holding on to my own electrons, but holding to the electrons when I'm colliding with others. So smaller things tend to be more electronegative. And in a similar fashion, for the force to be increased, I want the charges to be big as well. Remember, going across here, I'm actually going to pick up protons. Let's say lithium here has 3 protons, then 4 protons, 5 protons for boron. As I step across to the right, I'm picking up charges. As the charges and the Z effective increases, that would also increase my force of attraction. So long story short here, just like we said earlier, our radius is actually decreasing, going in that direction. Radii decreases. Remember, radii is just plural for radius. In this case here, we can actually say your En actually increases. Your ability to tug of war electrons, hypothetically, it would have been a covalent bond. When that tug of war gets to be really uneven, we might actually end up being ionic overall. So that's this property here of electronegativity. This is what decides whether you are ionic or covalent. Second property we're going to look at, although it has a very similar name to the one that we just did, it's a totally different concept. So this one here is going to be called an electron affinity. When you have an affinity for something, you have a liking of something. In this case here, we're looking at how liking of electrons are these atoms. We're going to use EA as a shorthand for that. Again, it sounds very similar to electronegativity, but totally different concept. I'm going to actually start writing out the technical definition. I want you to ask yourself, what does this definition sound like? It's something that we've actually gone over before. Electron affinity is the energy released when an electron is added to a mole of gaseous, again the word species is just general, I'm not specifying it's charged or not charged, it's just a gaseous thing, okay, at ground state. So we are looking at another physical characteristic here. We're starting to learn this electron affinity. What does this definition sound like? If you said ionization energy, you would be correct. Where the difference is, though, for ionization energy, although ions could be positive or negative, we had defined IE in yesterday's lesson. IE was, I'm coming in with a pair of tweezers, I'm grabbing electrons that are already there, and I'm trying to remove an electron. That's the direction. In this case, what I'm doing is, my metal is just sitting there, I'm not coming in with a pair of tweezers, I have a handful of electrons that are, sometimes we say they're at infinity. They have to be infinitely far away, or else your Coulomb attraction, they will sense each other. But they're at infinity, and all I'm doing is I'm going to try to force these electrons onto the metal, or the nonmetal, or whatever element it is. So the process is, instead of removing electrons and making things positive, I'm actually giving you electrons. When I gain electrons, that's called a reduction reaction. If I do that just for one atom, again, it's a really, really tiny value. So just like ionization, I'm going to line up an Avogadro number of these atoms, and I'm going to imagine adding a single electron to each one of these elements. Doesn't matter if it's metal or non-metal. This EA property tells you how liking is it for this electron. When energy gets released, remember, we're going to end up with lower energy. Lower energy means more stable. So let me just write out some representative equation here. We can take an element, usually they use metal for M or X for non-metal, but it really doesn't matter. Again, be really careful that it has to be gas, just like we did for ionization energy. This time, instead of pulling off an electron, this time what I'm going to do is I'm going to give it an electron. When this happens, an electron just gets added to the next shell that's available. I'm going to still be the same element, I'm still M, but suddenly I'm now an M minus. Just like ionization, you could have come back successive times, you could have come back multiple times. This one here is called the first electron affinity. For the very first electron I add, this is the amount of energy that gets released. If I similarly did second electron affinity, take M as a -1 as a gas, give it that second electron. Every time you electron affinity, it's just going to be one electron at a time. In this case here, second EA is going to end up making M -2 as a gas. And you can go on from there. So that's the notion of electron affinity. It is somewhat the opposite of ionization energy. First thing we need to talk about, just before we compare these successive electron affinities, is how the numbers actually end up looking. So if I go back to my table here, I'm going to do as an example, let's do the electron affinity for lithium versus the electron affinity for fluorine. Okay, so lithium's value happens to be -60. So Li, it's an atom like this. The EA value is quoted to be -60, whereas for fluorine is much farther to the right. We know that the size of it is fairly small. We're still energy level 2. I'm still shell number 2, but having about 6 more protons, it's going to end up pulling in the shells in tighter. The fluorine has a value of -328. In both cases, you'll notice the numbers are negative. Why the number here is negative, I think 348 was the number, kilojoules per mole. Why the numbers are negative is because we already said once the electron gets added, energy is released. We end up going to a lower energy configuration. Lower energy means more stable. So in this case here, you're going to note first ionizations, these ones here, first electron affinities are always exothermic. If you remember from your Science 9, Science 10, exothermic means it releases energy. By releasing energy, I go to a lower energy state. I end up becoming more stable. I end up liking it more. So in this case here, what you're going to find when you check that section 8 on the table, you're going to find they quote all the first electron affinities. You're going to quote all of them are actually negative. They release energy. When they release energy is if I have an electron, if I add this electron to lithium, it's a little bit strange. Lithium doesn't really want this electron, because if you thought about this reaction, it would be lithium is gaining an electron and suddenly becoming lithium minus. So I've never seen lithium minus before, but that's what this property here talks about. Lithium, in gaining this electron and helping to stabilize this electron, it ends up releasing off, it ends up giving off 60 kilojoules for the mole of lithium atoms that you add it to. So that number there is 60. Let's do the same process. Let's take another electron and let's imagine adding this electron to fluorine instead. This one here will look a lot more conventional to us. Fluorine is unstable by itself. If I give it that electron that it wants, it fills its noble gas configuration and ends up getting an F-. So naturally, this electron affinity property is a lot more useful for nonmetals than metals. But what I wanted to compare is, you'll notice, even though lithium doesn't necessarily want a minus, the electron affinity is still exo, just like a nonmetal is exo. So I'm just going to pretend I know that they're negative. How I'm going to define this here is I'm just going to look at the magnitude. How much does lithium want this electron? Lithium only wants this electron 60. It's able to get 60 kilojoules of stability when it adds this electron, whereas fluorine actually is able to get 348 stability, about 6 times the amount of stability from lithium. So in terms of just wording of this here, this gets a little bit weird. Even though -60 on the number line is actually bigger than -348, ignoring that negative for a second, just looking at the size of the number, I'm going to call 60 a smaller electron affinity than, say, the number 348, which is a larger or a bigger EA. Fluorine is more hungry for these electrons. It's able to release off more energy, become way more stable than, say, only lithium added it. That's how we usually define it, smaller and bigger. That usually gets a little confusing. Oh, are we including the negative this time or not including it? So usually the wording here, we'd rather say fluorine is more exothermic. It ends up releasing off more energy. You get more stability, whereas lithium, like all metals here, are going to be less exothermic. So the question here is, even though this metal here doesn't really want the electron, how come first electron affinities are exothermic? How come it should be a spontaneous process? How come these guys here will naturally gain the electron? What's actually happening here is sort of like a lesser of two evils kind of argument. In this case here, our electron is at infinity. So the electron is loose. Who knows what it's doing, right? The nonmetal definitely wants this electron, because for fluorine, it's part of the halogen family, so it has 7 valence electron. not only would it naturally be able to stabilize the electron anyways, but it has the added benefit, once you add one more electron, you filled up my last spot here, and now I can enjoy noble gas stability. I'm going to really want to do that because that's going to give me a lot of chemical stability. But what about the metal? The metal having lithium minus, lithium is an alkali metal, it only had one electron out of more shell. If I gain an electron, if another electron arrives at your hotel, it just ends up going into the next spot that's available. That's not close to a noble gas. That's not close to filling its shell. How come this one here actually wants to also will stabilize when it gains this electron? In this case here, I use an analogy. Let's say lithium here is your family or is your home. Your family may not necessarily want you as the electron close by, sort of living at home or actually staying home, but it's sort of playing the odds here, sort of saying, well, who knows what you're doing when you're out in the neighborhood and you're maybe causing trouble outside. I'd rather you be home. If you're home, at the very least, there's protons in my home that can actually stabilize these electrons. So again, it's a lesser of two evils. It's not necessarily that the metal actually wants the electron. I don't want to become lithium minus, but the alternative is worse. If the electron was just loose by itself, who knows what kind of trouble it's getting into. I would rather grab that first electron. Upon gaining that first electron, I'm able to give it some measure of stability. I'm able to stabilize it to my core, attract it to my nucleus, and at least I can keep my eye on you. I can keep my eye on those electrons there. So in that case there, even metals don't necessarily want it. It is able to release off a little bit of energy, but definitely for nonmetals, they release way more energy than, say, the lithium. So that there is electron affinity. As you compare successive electron affinities, as you add one electron, then you add another electron, even though the first one was always exothermic, it's always going to become more stable, you'll notice after I electron affinity, I become negative. If there's another electron that I now want to add, there's going to be also added repulsion between the second electron and my anion forming. So what's going to usually happen is, although the first electron affinity is exothermic, usually the second one, you really need to apply energy. This, maybe your sibling really doesn't want to come home. You really need to grab your sibling and actually pull him home kind of against his will to be attracted to the core. For a few of these elements on the periodic table, electron affinity here, we don't have all the numbers, but for a few of these, they first track for you the first electron affinity. Sometimes they give you the second. Say for oxygen, when oxygen gets its first electron, O gas gains an electron, becomes O minus. The value they give me here is negative 141 kilojoules. When I'm already O minus as a gas and I want to gain one more electron, this is a little bit strange because O minus 2 is its natural charge. That's when I get that noble gas stability. But if you look at this electron affinity property, the property is actually a positive 753. I need to input energy 753, drag the second electron, overcome the negative that we already had from the O minus to force the electron. Yeah, I'll get some of that money back or some of that energy back when I get the stability, but you notice that it's fairly positive. So for a few of these, you're going to see second electron affinity is typically going to be a positive value. Again, we need to come back and we need to talk about, this is a periodic trend. We can see the numbers, especially remember when it says state and explain. State just means look up the value. Look up the right table and make a comparison. What property of the atom will actually make it want the electron more or able to release more energy? It actually has to do with this measure of stability. If I'm able to stabilize the electron more, if there's more attraction to the nucleus, the electron will have an easier time adding to the outer shell. When that electron is closer to the core, that increased force of attraction will keep a hold on the electron. Any extra energy that the electron had when it was by itself is now going to be released off. So in terms of size here, again back to our periodic trend, we have our rough periodic table. If you know about the size, if you know the size of the atom actually shrinks, if I had a bunch of electrons and I wanted to add electrons, say I add an electron to something that's big versus add an electron to something that's small, in which case will I be able to release more energy? Again, the principle that we talked about was a Coulomb. F is equal to kq over r squared. If you're going to want a strong attraction between the center protons and the electron that I'm adding, what you're going to want is you're going to want, again, a small radius, because that's an inverse relationship here. The tinier that I am, the stronger the attraction is going to be. And in terms of charges, let's say I go left and right, I'm going to want to have higher charges. So let's just write this down in words here. The attraction is stronger when Z effective, or any charges for that matter, when Z effective is big and when radii is small. And based on this trend here, we already had said the radius shrinks going up into that corner there. Radius decreases. Remember, you still need to quote, it's because we have less shells, or it's because we have higher Z effective. Okay, you still need to quote those as the reasoning. But as I get tinier, when the electron gets added to something that's tiny, it's a lot closer to the core. Small radius would mean a great attraction for it. Compare that to this situation. When my cesium or my francium is really, really large, like most of your metals are, they typically are very big atoms anyways. When I add electrons to them, I'm not actually able to stabilize it as well. I still release energy. It's still better than the alternative of letting this electron just sort of loose by itself, but it's not going to release nearly as much energy. We saw for lithium it was only a -60, whereas fluorine was some -350 or so. Right? So far we've done two properties. Electronegativity was this measure of tug-of-warring. You have to mention in a covalent bond. Electron affinity, which sounds very similar to electronegativity, but it's a totally different concept. In some sense, it's the opposite of ionization energy. Make sure you still have all those technical notes. Make sure you're doing it to a mole. Make sure you're doing it for gaseous. In the equation, make sure you have these gas symbols. Right? And one last property that we're going to do in this section, we're going to do a trend on melting point. Now, just right from the start here, when we deal with melting point, you can even do boiling point here as well, MP or BP. You're going to find that the trend in melting point is not very well defined. It's not as nice as we had here. Sorry, I forgot to write the arrow for you. As the radius decreases, you can actually say in terms here, the EA increases. Right? So I'm looking, sorry, I can't spell here. EA increases. So we go from numbers like the -60 from earlier to -348. And I'm saying, well, how is that an increase? -348 is a tinier number. Remember, I already know things are exothermic, so I ignore that negative for now. And what I do is I look at the size of the number. I get 60 kilojoules of stability for this lower element here. I get 348. I get way more stability. It's more exothermic as I become tinier. Okay, so that's just a wording there. So these trends here, electronegativity and electron affinity, you see that they have, like, if I go in one direction, I have a general expectation of what happens to these numbers. The problem with melting point is they do increase to a certain extent, but depending on what type of bonding that I'm actually doing, I'm actually going to need to talk about these separately. Case in point here, we're going to look at the melting points. So this is section number 7. We have been dealing with section 8 here. But section 7 here likewise has a periodic table. It quotes the melting point here in Celsius. I think some of your tables now quote it in Kelvin. Doesn't really matter. What you're going to have here is melting points on the top of every element box. So you'll notice, just taking a look at the numbers here, I go from melting at 63 degrees to 840 to 1000 something. We see there's an increase, but slowly, after it increases to a certain point, let's say 419, it ends up shrinking. And it gets bigger. And over here, oh, it's really, really tiny, and it gets bigger. So the melting point trend is not nearly as good as the other two properties as we've done so far. So to understand why this is, we still need to know the trend, but just caution that it's not going to be as nice as the ones that we do. Make sure we know the definition first. Melting point is the temperature. You cannot say it's the temperature when things melt, because that's using the same name. It's the temperature when solid becomes liquid. Sometimes they call that process fusion. Again, that's another fancy word for going from the solid state to liquid state. It is a physical change because we're going from being tightly packed, the particles themselves aren't changing, heating it up enough so that we overcome those intermolecular forces and the particles themselves are now in the liquid state. What we need to do in studying the melting point trend here for the periodic table, in trying to find the periodic pattern here, we actually need to separate our periodic table into 3 segments. Because melting point here, it's going to depend on the type of bonding. It depends on what type of bonding we're using. So what I'm going to separate here, we knew the periodic table was already divided by a stair step. I'm going to separate into category A. Category A are mainly going to look at metals. We're going to refer to these guys here as metallic bonding. The things that do metallic bonding, we'll see what that is, and we'll see what happens to the melting point. We're going to look at category B next. Category B are looking at our nonmetals. our nonmetals, they typically do what's called a London force, or even a induced dipole kind of force. Kind of funny name is van der Waals forces. And then we're going to finally end up with this sort of metalloid region here. That's going to be category C. And these ones here are usually going to be giant covalent structures. Okay. So because the type of bonding is actually different depending on where I am on the periodic table, my melting point trend, when it increases or decreases, will actually be different. We're going to touch on this a little bit more in the next chapter, but just in a nutshell here, let's start off just looking at these metals. What is metallic bonding? Metallic bonding is the electrostatic attraction. Electrostatic When you see the term electrostatic, it just means a Coulomb attraction. It's the KQ over R squared kind of attraction that we're dealing with. Electrostatic attraction between your positive nuclei and a new name here, and delocalized electrons. Okay. So one thing I want to just emphasize here, as I just explained to you what delocalized electrons are, let's start off with an ionic compound. Ionic is not metal. Ionic may be something like NaCl. We knew it ended up forming a lattice. We ended up getting, let's say, Na+, Na+. I'll draw these in green. And then let's do the Cl-, Cl-. For an ionic bond, it's not so hard to see this electrostatic attraction. Oh, yeah. Sodium is positive, chlorine is negative. That's an ionic bond. What if I compare it to the metal case in this situation? For a metal like sodium, how does my metal picture differ from this sodium chloride? In the metal example, we actually we still have a structure, we still have a solid. Most metals are solids. But what we're going to have is we're going to have a bunch of just sodiums. There's no chlorines in sight. It's just metal. Because it's all metals here, we don't have any electron transfer. We actually don't get any ions in this situation. And yet, this metal here is still able to hold itself together. The thing that's keeping it as a solid, we do still have something that's positive. In this case here, it's not the sodium ion, it's not the Na+ that's positive. It's actually the nuclei have a bunch of protons. That's where I have this notion of positive nuclei. Those nuclei are still there whether I have chlorines or not. And it's their attraction for electrons. Now this already works here. We know positive likes negative. So sodium has a good hold on its electrons. Every single atom has a good hold on its electrons. And yet what we're going to do here is for this substance to actually stay together, this positive charge not only needs to attract its own electrons, it actually needs to attract electrons on the neighbors. That's the only way one atom is actually going to stick with the other atom with its neighboring electrons as well. So in this case here, we're not talking ions. We're not talking sodium plus attracts Cl minus. We're talking the attraction between the positive centers. We are solid, so these centers are sort of stuck in place. They're just doing really minor vibrations. And attraction with electrons. I actually qualified it as what are called delocalized electrons. A localized electron would be an electron where you can really put your finger on it. That's where the electron is. We're going to see more so in chapter 4. Because atoms tend to have a very large radius, the electrons, metals tend to have very low ionization energy. It's really easy to remove the electron, but they have a very low EA as well. Not easy to regain the electron. So essentially, I'm thinking here, even though every sodium is supposed to have 11 electrons around it, because it's a relatively large atom, it has a hard time holding on to its electrons. Maybe I should say it has a hard time hanging on, so it's really easy to pick off the electron. You give it a bump and the electron comes off. The electrons actually feel really unloved in this situation. The electrons actually say, fine, if you don't want me around here, I'm going to end up swimming. I'm going to end up going through the bulk material. That's actually what makes metals actually conductive. Whenever I have charges that can move around, it's conductive. But in this case here, that's what I call delocalized electron. It is still going to be the attraction between the positive centers and the delocalized electrons, the electrons that just happen to be swimming around it. That's what's keeping the metal together. At the end of the day, this is a Coulomb attraction. So if you think about F is equal to KQ over R squared, for these attractions, positive and negatives to interact better, for the attraction for the atoms to hold themselves together better, what we're going to want is we're going to want high charges. Remember, that's proportional to charges, and we're going to want small radius. Right? So if you look at the size of the atoms, if you look at this segment A here, we know about our metals. We go from big. As you go across, the Z effective increases, I shrink this way. As you go upwards, we know that the size of the atom, I lose number of shells, I get smaller. I would expect, because these radii are tinier, and also the charges are bigger, I would expect these to have a higher melting point. So in this case here for metallic bonding, melting point sort of increases towards the middle of the table, and that is verified by this chart here, starting with something that's really big. Francium here already melts at 27, but as I sort of head this way on the table, I get 920, 24.7, 1246. It ends up increasing as I go towards the middle. This is only true for the metallic bonding part, though. Now let's switch over to the nonmetals and the London forces. We know already the London forces are fairly weak, because if you look at the regular state of matter, if I look at fluorine and I look at chlorine, these ones here are actually already gases at room temperature. That means by room temperature, this one here has already gone and melted and even vaporized, even boiled already. So that means I know, in general, these tend to have very low melting point and low boiling point. This time, for this side, we actually have the melting point sort of increasing towards the middle. The reason for that here is when we look at London forces a little bit more detail, what we're doing here, let's say I have a sample of solid fluorine. Really weird, because fluorine, I would imagine, is going to be a gas already. But if you can cool it down and get liquid fluorine and then cool it down more, I can get a solid chunk of fluorine. I know fluorine is diatomic. I know fluorine is an F2 molecule. Again, we're talking in electrostatic attraction, a positive negative attraction. All I need to identify for you here is what are these London forces. The London forces are, again, you can say electrostatic attraction or Coulomb attraction between. The only thing positive in this picture are the nuclei again. But unlike the metals, the atoms of the nonmetals are tiny. They're not going to have delocalization. We're going to have the attraction. The positives inside the nuclei are attracting its own electrons. But they're not actually just bounded to their own molecule. The positive on this first molecule is attracted to electrons on the neighbor. It actually doesn't form a bond. They don't form a stick. They don't form an actual glue, an actual hold on them. But there is some measure of attraction. But what we know is because these are gases at room temperature, we know these London forces here, these in-between forces, which we call London forces, these forces are relatively weak. So Coulomb attraction between positive nuclei, I'm just going to call them and neighboring electrons. These are electrons that happen to be on other particles beside me, and they're relatively weak, so that's why all nonmetals doing this type of bonding are going to be really easy to vaporize. Be really careful when I'm melting this here. Notice once I actually melt it and actually get liquid fluorine, you notice that it's still diatomic. The covalent bond itself is actually still intact. I'm actually not trying to destroy the covalent bond. I'm actually trying to just separate one molecule from another molecule. So in some sense, it's unfair. In the metal case, it was actually breaking apart metal to metal bonds. In this case here, it's just separating. How this one here is side by side. We call these intermolecular forces. Sometimes you call them van der Waals forces, a little more in chapter 4. So neighboring electrons. Let's compare the fluorine case here to iodine. Iodine, even though it's a nonmetal, it's actually a solid. What would that imply in terms of the melting point? That means in this case here, while we're still at room temperature, this one here has a much higher melting point, as well as BP boiling point. For iodine, it's a much larger atom. Now what you would imagine here is, well, Coulomb says, if the radius is big, of course I don't attract as well. That is definitely true. The positive centers on these iodines here are having to reach out quite a bit farther to touch the electrons on the neighbors, so the attractions are going to be weaker. But at the same time, one other thing is different. Every single fluorine only has, I believe it's, is it 9 protons? 9 protons. So 9 positives that are attracting, whereas iodine is 53 protons. So what's going to happen is, although dollar for dollar, these charges here are going to be weaker, I'm having to reach out farther, but I'm having a whole lot more protons. I have a whole lot more electrons that I'm attracting to. Just the sheer number of attraction, the sheer number of ways I can connect with my neighbor is actually so much so increased. It's going to cause much more higher temperatures to actually separate one molecule from the other molecule. So in this case here, just make a note to yourself. For London forces, even though they are weak overall, they are stronger with more electrons. And how we usually track more electrons is we usually track higher molar mass. Yes, mass doesn't necessarily have to do with electrons, right? Electrons really have no mass, but if we have an atom that has a high molar mass, chances are your high molar mass is because you had more protons. More protons typically also means you have more electrons. So in the case here where we have more charges, as you go downwards, although the size of it does slowly get bigger and bigger, those Coulomb forces get weaker and weaker, but having more charges means I attract it much stronger. Just to finish off here, segment C here. Segment C has the best of both worlds. It sort of has the lattice structures like ionic or metallic bonding, and it's much, much stronger than just really weak London forces. It's still covalent. Dollar for dollar, a covalent bond is actually stronger than an ionic bond. But what's going to happen is we're actually going to have a covalent bond that sort of repeats again and again, just like in a lattice. In chapter 4, we're going to look at diamond as an example. Diamond is actually just pure carbon. Carbon is going to be one of these ones that are really, really hard to melt. If I start looking at diamond structure, this is category C here. They do call them giant molecules or giant covalent networks. Network solid. Sometimes they call it that. So diamond is actually, just as an example, diamond is actually just pure carbon. It's just C. Carbon can bond to itself. So far we've seen that with the diatomic. For other diatomic molecules, it's just 2. But for diamond, it actually repeats this bonding. Diamond actually is bonded to 4 other carbon neighbors. Every one of these carbon neighbors are similarly bonded to 4 other carbon neighbors. This carbon here is also bonded to 4 other carbon neighbors. You can see that this picture here is getting really complicated really fast. In trying to melt diamond, what we're trying to do, we're not just trying to separate one molecule from the other molecule, like in the London force case. We actually are physically coming in trying to break this covalent bond. Not just this one, this one, this one, this one, this one, this one. Because I'm having to break a ton of covalent bonds, it's going to be a ridiculous amount of temperature that you heat it up before it actually starts melting. So all that to say, the melting point trend is fairly bad. You do have the melting point table here on your chart. Essentially, for metallic case here, melting point increases towards the middle. London force cases, melting point increases toward the middle. These ones here happen to have the highest melting point. You don't need to memorize any of that because you do have the data booklet, but at least that's the periodic trend we're going to deal with. We'll flesh this out a little bit more on tomorrow's lesson and then switch over to some chemical properties. Thanks, guys. Take care.